Assalamu alaikum. In this lecture we are going to study about the method to increase the surge impedance loading. So from the last lecture we know that SIL is equal to VL square over ZC. So this is the line voltage squared divided by the surge impedance. So in order to increase the surge impedance loading, either we have to increase the transmission line voltage or we have to decrease the surge impedance of the line. But the increment of VL is expensive because we have to use the larger transformers. So rather than increasing the VL, we will try to reduce the surge impedance of the line. And in order to decrease the surge impedance, actually we are going to try 4 different methods to check that what will happen to the surge impedance loading if we will add a series inductor or capacitor to the transmission line, or parallel inductor or capacitor to the line. So what will be the effect of these 4 integration in the transmission line on the surge impedance loading? So in order to assess the surge impedance loading, we have to use 2 of the formulas, which are ZC is equal to under root L over C. This is the formula for the surge impedance, and gamma, which is a propagation constant, is equal to under root LC. Because we are going to add inductor and capacitor in series or parallel to the transmission line, so there will be an effect on the surge impedance value, which is the combination of inductor and capacitor in the formula, and also on the propagation constant, which is under root LC. We want to decrease the surge impedance, which will increase the surge impedance loading. But with the change of inductor and capacitor, there will be a change in the propagation constant as well, and this propagation constant should be less because it comprises of 2 parts, alpha plus beta j. This alpha is the attenuation constant and this beta is the phase constant. So these 2 constants actually tell you about the changes in the voltage magnitude and phase change throughout the line. Also, they also tell you about the current magnitude and current phase change throughout the line. So we have to put a check on the propagation constant as well in order to decrease the surge impedance of the line. Starting from the first consideration, which is series inductor. So in the first case we are going to use a series inductor in the transmission line, and if you remember from the models of the transmission line, we have a impedance in series branch and admittance in the shunt branch, right? I'm using the T model. So if I'm going to add the inductor, it will add up to this particular impedance, right? So there is an inductor and the new one that I'm adding will be this inductor. This is new inductor and this is the old inductor, right? So this, the inductance of the line will increase, right? So if inductance of the line will increase, surge impedance will also increase because the inductance is in the numerator. So if inductance is increasing, the surge impedance will also increase. So if surge impedance will increase, the SIL will decrease, which is not desirable. Also for the propagation constant, if the inductance is increasing, the propagation constant will increase, which means the attenuation of the line will increase. Which is not desirable. We cannot use a series inductor in the transmission line in order to increase the surge impedance loading. Similarly, for the parallel inductor, the inductor will be in parallel with the capacitor, which is in the shunt branch. So this inductor will nullify the effect of this capacitor. So if the inductance is increased in the parallel branch, the capacitance will decrease, which will increase the surge impedance. So if surge impedance is increasing, surge impedance loading will decrease, which is not desirable. But for the propagation constant, the value will decrease, because if the capacitance value is decreasing, the propagation constant value will decrease. So it means that attenuation will decrease. But the goal of this lecture is to increase the surge impedance loading. So we will not use a parallel inductor in the transmission line in order to increase the surge impedance loading. Yes, we are getting some benefits, that one of which is that attenuation is decreasing, but on the other hand, the surge impedance loading is decreasing. Now we will use a parallel capacitor. In case of parallel capacitance, the capacitance will increase, and that will decrease the surge impedance. That will in turn increase the surge impedance loading. If the capacitance in the shunt branch is added, then in the model we already have a capacitance here. So if there is another capacitance added in parallel with this capacitance, the overall capacitance will increase. So if capacitance is increased, it means this capacitance is increased, so surge impedance is decreased. So if surge impedance is decreased, the surge impedance loading will increase. That is desirable, right? And with the increment of capacitance in the shunt branch, the propagation constant will also increase, which is not desirable, because with the increment of propagation constant value, the attenuation in the line will increase, which is not desirable. So in the last case, we have series capacitor. Now with the addition of capacitor, we already have an inductor in the series branch, and this capacitance will nullify the effect of this inductor, which means the inductance will reduce. And the formulas of surge impedance loading, ZC and gamma, which are VL square over ZC under root L over C and under root LC. So if inductance is reduced, surge impedance loading will reduce, and that will give rise to the value of surge impedance loading. So with the decrease in the value of inductance, ZC will decrease and surge impedance loading value will increase, which is desirable. And with the reduction of inductance value, the propagation constant will decrease, means the attenuation will decrease, which is desirable. So in order to increase the surge impedance loading of the transmission line, we have to add a series capacitor in the line. That will increase the surge impedance loading and also reduce the attenuation of the line. So there will be less change in the sending end and receiving end quantities, either for voltage or current, in terms of magnitude as well as the phase value. Thank you.